Welcome to our presentation. We are a group of two. My name is Kumar Dash. Along with me, my co-authors, MD Saidur Rahman. Before I start presenting our work here, I would like to thank our professor, Dr. Mohsin Jamil, for his guidance throughout the semesters. So the topic we have chosen is the integration of renewable energy and its impact analysis. We have considered Saskatchewan in our project prospect. So in this section, we'll be discussing about a little bit of introduction and the background of this project, why we have choose this project, how we have designed our methodology to complete this project, how we have designed the system so that we can get the best result out of it, and the result and discussion finally with a conclusion. In this introduction part, we are saying that the Saskatchewan distinguishes itself as an international focal point for the multi-faceted generation of energy resources encompassing crude oil, natural gas, coal, uranium, biofuels, geothermal energy, wind energy, and hydroelectric power. In the year of 2021, the aggregate assessed value of oil and gas production surpassed 3 billion US dollar. Electricity generation in Saskatchewan predominantly relies on fossil fuels, with approximately 81% of the total supply coming from this source. Among the fossil fuels, natural gas constitutes around 40%, coal comprises approximately 41%, and a minimal amount of petroleum is employed in remote off-grid communities. The remaining 90% of the electricity supply is sourced from renewable energy, primarily through hydroelectric power. The typical cost of electricity for household in Saskatchewan stands at around 20 cents per kilowatt hour. In the year 2020, Saskatchewan greenhouse gas emission reached a sum of 65.9 million metric tons of carbon dioxide equivalent. Per capita greenhouse gas emission in the province stand as the highest in the Canada among all the provinces, and 55.9 tons of carbon dioxide emission, which is 200% to more than 200% higher compared to the national average of 17.7 tons per capita. The Paris Agreement aims to limit the rise in the average global temperature to significantly less than 2 degrees Celsius above pre-industrial levels. Canada's federal government unveiled net zero electricity grid by 2035. It is their mission. However, such power stated that the objective is technically, logistically, and financially unattainable. Why we choose this project? So there are certain reasons why we choose this project. The current pertinent literature highlights Saskatchewan's renewable energy potential. Saskatchewan transition from the dominant fossil fuels to renewable energy requires more holistic planning and infrastructural development from the key stakeholders. Some proponents argue that establishing more carbon capture and storage facilities will reduce carbon dioxide from the environment, but the amount of carbon dioxide reduction is far less than emission. Renewable energy constitutes less than 20% of Saskatchewan's total electricity generation, and it is evident that Saskatchewan will not meet Canada's net zero electricity grid by 2035. To achieve this milestone, we believe that net metering community-based electrical grid will be an alternative option. In this project, we will conduct analysis on Saskatchewan renewable energy prospect based on the province residential sector with various combinations of solar energy, wind energy, and grid electricity. So finally, the model we have designed, that is a combination of solar, wind, and grid power. So in this methodology section, we started the project, we have gone through all the literature review related to this project, and we tried our best to get all the information. What is the scope of doing this project in Saskatchewan? Then we identified lots of challenges, and there are some opportunities as well, but it's not limited with the threats. So we collect all the data from such power to use that data in the Homer Pro for our simulations. Once we got all the data, we implemented all those data in the Homer Pro simulations. We tried to find out each solar gives us the optimized result. If no, then we find out the best possible scenarios. At the end, we get the total result, and we analyze this result, and finally we prepared our report. So in this design sections, what we have considered? We have considered a very small house which is around 1600 square feet. We think that the three people lives there, and it has definitely bedrooms, it has heater, it has freezer, it has dryer and washer, along with the light bulbs. So these are our consideration for a house to design our model. In this picture, we are seeing that the monthly average of solar data of Saskatchewan, we find that the maximum average solar power is around 8.8 kilowatt per meter square in the Saskatchewan, which is in the month of July, and this is the summer month for them, and the lowest power generated is 0.2 kilowatt hour per meter square in the month of December. We can see there is a trend during the month of winter. It has lower generation level, but when the temperature start getting up, the production of solar power is increasing from the month of April, and it reached to the peak at the month of June and July. So this is the calculation that we have done before incorporating all the data to the Homer Pro simulation. So the average solar GHI of Saskatoon is 6 kilowatt hour per meter square per day. The energy demand for the house that we have chosen is 11.25 kilowatt hour per day. The efficiency of solar model is 13.7%. 2-axis tracking efficiency is 70%. Each module that we have chosen, the PV panel, it has an area of 1.456 meters square. So the solar panel area size is altogether 19.55 meters square. So in a house of 1600 square meter area, it is easily possible for us to accommodate all those panels on the rooftop. And for the wind speed, we know that the average wind speed is 4.8. So the capacity that we need for the house is 288 kilowatt. So this is our Homer Pro system architectures. In this system, we see that the grid power connected in with the AC bus along with the wind power. Here we have chosen 650 watt, though we have selected the capacity to 88 watt, but this is the lowest size for the wind category. We see that the electrical load is 11.25 kilowatt hour per day, and the peak load is around 2 kilowatt at the peak time. We use a system converter that will actually convert the DC power received from the solar panel to the AC panel. And the solar model, the solar PV panel that we have selected is CS6K295 that we have chosen for this project. So this is the result that we have found in after doing the simulations. In this result, there are different options. So all these options actually suggesting us a hybrid model. But among all those models, we find that the first model with a combination of grid and the solar is the best model for our considerations. it is showing that the net present cost is the lowest one among all others model, which is around $7,600. The cost of energy is around 12 cents. There is a small bit of operating cost. That operating cost is basically for the grid. There is an initial investment for the solar panel and the storage, which is showing around $1,700. So this is the best model for us, and we're gonna talk about this model in the further section also. So the basic model that we chosen is around 2.61 kilowatt from the solar panel. Our storage size is 0.678 kilowatt, and the grid power is connected with that. So in this sections we see that the it is evident that the capital expenditure incurred for the solar and the system converter, there was no capital cost for the grid. Initial capital, as I said, is $1,700 for the system, and the uh, operating cost for the system is around 5,000 US dollar. So the impact of economic analysis on the cash flow of the system was clearly apparent during the replacement of the system converter, which occurs at 10 years interval. So the grid has a consistent operating cost throughout the year. However, the solar has some replacement cost for its converter every after 10 years. So this is all about my presentation. The next part will be continued by my co-authors, Mr. Saidur Rahman.
Thank you, Vasu. So, this is the output power of solar PV, and the rated capacity found 2.61 kilowatt, and it can provide maximum output 2.95 kilowatt. Mean output power was found 10 kilowatt hour per day, and the total capacity factor, that means how effectively it converts sunlight into electricity over time, and it was found 16%. And its total production was more than 3,500 kilowatt hour per year, and notably its PV penetration was found 89%, and it can operate more than 4,000 hours in a year. And this is system converters output, and this rated capacity was 0.678 kilowatt, and mean output was 0.2 kilowatt, and its total hours of operation was same as solar PV, that is 4,000 hours in a year. Its capacity factor was found 33%, and efficiency was 93%. And this is yearly time series chart of economic model. Here we can see there is a stark difference between grid purchase and grid sales, and we observe that grid sales increased during summer period, and this makes sense, as during summer there are more sunlight and more solar penetration, which ultimately increases solar PV's output power. And this is monthly electricity generation, where it was evident that electricity generation increased from month of April to September and decreased from October to December. Here is an electrical summary of the economic model, and we found that the total energy purchased from the grid was totaled 2,908 kilowatt hour, and grid sales grid sold to energy sold to grid was calculated was found 774 kilowatt hour, and the need purchase, that means grid purchase minus grid sold, was 2,133 kilowatt hour, and the respective energy charge was calculated $397. Right now in Saskatchewan, the residents have to pay monthly more than $300 for the utility bill. So residents can, if they employ or if they adopt this solar PV model on the rooftop, they can significantly reduce their utility bill and allocate resources to their financial reserves. This is time series plot of excess electrical penetration, penetration to grid sales, and this is excess electrical production versus grid sales, and we found that the excess electricity is that unmet energy we found 1537 kilowatt per year, which is 23% of total generation. That means we have a significant amount of energy we can utilize, or we need to harness this unmet energy. And this is instantaneous renewable output percentage of total generation, and which reflects the penetration, the proportion of electricity generated at a particular moment by renewable sources compared to the total electricity generation from all sources. This key performance indicator is crucial for assessing the system's reliance on renewable energy at specific times. This shows that the economic model's instantaneous renewable output percentage was 55.7% of total generation. That means the renewable sources contribute a bulk portion of the total electricity generation. And this is instantaneous renewable output percentage of total load, which reflects that the proportion of electricity demand made by renewable sources at a specific moment compared to the total electricity demand of the system. This is essential for evaluating the system's ability to rely on renewable sources during different operational scenarios. This indicates that the economic model's instantaneous renewable output percentage was 70% of the total load. This is cumulative discounted cash flow, which is shown here, and we found that that our economic model is showing a very good result, and we found that the sum of discounted cash flows over the entire project lifetime, and here we found for our economic model internal rate of return was 9.74%, return of investment was 6.5%, and its discounted payback period was 14.3 years, where we can easily found those two curves intersect here, and its simple payback period was only 7.2 years. So this is the financial comparison. We found that for our base model, where we considered for only grid, the net present cost was $8,306, and for our economic model, we found 655. So the majority of this net present cost contributed by solar PVs and system converters initial cost, and we found that and which was a total almost $1,500, and the rest of the amount was for the grids operational maintenance cost. And for the capital expenditure for the base model, as there is the infrastructure is already there, there is no capital expenditure. But for economic model, it was total $1,798. Operational expenditure mostly from grid, which is total 642, and for our economic model 452, which is also from the grid operational maintenance cost. The levelized cost of energy, that means the per unit cost per kilowatt hour. So we found for our base model $0.157, whereas our economic model we found just only $0.11. The CO2 emission we found for our base model 2,595 kg per year, whereas our economic model contributed 1,838. And the reason of this, which is almost 23%, 29% lower than our base model, and the reason is because there are 2 times replacement of the system converter during the whole tenure of the project. And in conclusion, we'd like to say that we found that the combination of grid, solar, and system converter gave us the optimum results for the in the residential sector of Saskatchewan, and the per unit cost is we have just got only $0.11 per kilowatt hour, which is 23% lower than the base model. Instantaneous renewable output percentage was 55.7% of total generation, and economic model fulfilled 75% of electricity demand, and the total electricity generation was 6,565 kilowatt hour per year. And we also found the excess energy was 1,537 kilowatt hour per year. And authors believe that successful execution of the project can add more value in the ventures of the renewable energy sector in Saskatchewan. And we found that to harness more renewable energy from this economic model, we can in our future works we recommended P2P energy trading and also energy storage facilities so that we can harness more renewable energy. And CO2 emission, we found that 29% lower than the base model, and authors expected that this could be a this could be a more this project can contribute more significant for moving towards for eco-friendly and sustainable energy environment in Saskatchewan. And these recommendations aim to minimize energy wastage, ultimately contributing to the attainment of sustainability objectives of the province of Saskatchewan. So that's all from our side. Here is our email address and also our LinkedIn profile, so that if you have any concerns, feel free to reach us and we'll try our best to address your concerns.